Hello dear students, we are going to solve some numerical problems related to photoelectric effect today. At first we review the related formulas. First, work function phi naught is equal to h into f naught, which is h c upon lambda naught, where h is Planck constant, its value is 6.625 into 10 to minus 34 joule second. F naught is threshold frequency for the given metal. Lambda naught is the threshold wavelength for the given metal. Now the maximum kinetic energy of emitted photoelectron is given by the relation Ke max, which is half mv max square, which is f h into f minus phi naught. Here m is mass of electron and v max is the maximum velocity of emitted photoelectron from the metal surface. Third formula, if V naught is the stopping potential, then kinetic energy K max, maximum kinetic energy, is equal to E into V naught, which is half mv max square is equal to h f minus phi naught, where V naught is the stopping potential. Next, 1 electron volt is equal to 1.6 into 10 to minus 19 joules. Here is the charge of electron, which is 1.6 into 10 to minus 19 coulomb. First problem is find the change in stopping potential when the wavelength of radiation is decreased from 400 nanometer to 300 nanometer from the same surface. Planck constant is given to be this much. Now solution. Let us understand this question from or with the help of this diagram. Suppose this is the given metal surface having work function phi naught. In first case, wavelength of incident photon is lambda 1, then kinetic energy of emitted photoelectron will be K1, suppose this is K1, and when the same surface is illuminated with another photon of wavelength lambda 2, then kinetic energy will be Ke2 of photoelectron. Here lambda 1 is 400 nanometer. Nano means 10 to minus 9. 400 10 to minus 9 meter, and lambda 2 is 300 nanometer means 10 to minus 9 meter. Now we have to find the change in stopping potentials, means we have to find delta V naught will be how much, means change in stopping potentials. In these two cases. Now because the surface is same, therefore work function will be same as the surface is same. In both cases, therefore phi naught or work function will be same. Now in first case, therefore in First case, Ki1 will be equal to H C upon lambda 1 minus phi naught. Suppose this is equation 1. And in case 2, case second, Ke2 will be equal to Ke2 will be equal to Ke2 will be equal to Hc upon lambda 2 minus pi naught. Suppose this is equation second. Now from equation 1 minus 2 we get K1 minus K2 will be equal to phi naught cancels out, Hc is common, so we get Hc 1 upon lambda 1 minus 1 upon lambda 2. And we know that Ke is equal to E into V naught, so we can write E into V naught 1 minus E into V naught 2 is equal to Hc 1 upon lambda 1 minus 1 upon lambda 2 common. Therefore, B naught 1 minus B naught 2, that is change in stopping potential, into E will be equal to Hc 1 upon lambda 1 minus 1 upon lambda 2. E goes on the right hand side. Therefore, we get, this is change in stopping potential, means delta B naught, you can say B naught 1 minus B naught 2 as change in stopping potential, which is Hc upon E 1 upon lambda 1 minus 1 upon lambda 2. Now putting the values, we get H is 6.62 into 10 to minus 34, C is 3 into 10 to power 8, E is 1.6 into 10 to minus 19, into 1 upon lambda 1 is 400 into 10 to minus 9 minus 1 upon 300, 1 upon 300 into 10 to minus 9. On simplification, we get the change in stopping potential as 1.034 volt. 1.034 volts. Second question is, a clean nickel surface of our function 5.1 electron volt is exposed to light of wavelength 335 nanometer. What is the maximum kinetic energy and velocity of emitted photoelectrons? Solution: here we have work function phi naught is equal to 5.1 electron volt, which is 5.1 into 1.6 into 10 to minus 19 joules, or if 8.16 into 10 to minus 19 joule. wavelength of incident photon is 335 nm, 335 into 10 to minus 9 meter. First we have to find Ke max of photoelectron, and second V max, maximum velocity of emitted photoelectron. Now Einstein's photoelectric equation is H into or Ke max is equal to Ke max, which is half mv max square. Max is equal to Hc upon lambda minus phi naught. Values of Hc lambda phi naught you can put H as 6.625 into 10 to minus 34, C 3 into 10 to power 8, lambda 335 into 10 to minus 9, minus phi naught. Phi naught is 8.16. 8.16 10 to minus 19, and on simplification it gives the kinetic energy as 2.91 into 10 to minus 20 joules. Now the second part is Ke max will be equal to half mv max square, which gives V max as under root 2 Ke max upon m, where m is mass of electron. Now this is 2 Ke max is 2.91 10 to power minus 20 upon mass of electron is 9.1 into 10 to minus 31, and on simplification we get the velocity, maximum velocity as 2.52. This gives 2.52 into 10 to power 5 meter per second. Question number 3 is sodium has work function of 2 electron volt. Calculate threshold frequency. Now we know that work function is equal to H into F naught. Therefore F naught will be equal to phi naught upon H. Phi naught is given to be here. Phi naught, which is work function, is given to be 2 electron volt, means 2 into 1.6 into 10 to minus 19 joule, which is 3.2 into 10 to minus 19 joules. Therefore threshold frequency F naught is what? This is threshold frequency. So 3.2 into 10 to minus 19 divided by Planck constant 6.62 10 to minus 34. On simplification we get threshold frequency as 4.8 into 10 to power 14. 4.8 into 10 to power 14 Hertz. Next question. Radiations of wavelength 5000 400 angstrom fall on a metal whose work function is 1.9 electron volt. Find the energy of emitted photoelectrons and stopping potential. Here we have lambda as 5400 angstrom, and as you know 1 angstrom is equal to 10 to minus 10 meter, so it is 10 to minus 10 meter, and work function is 1.9 electron volt, which is 1.9 into 1.6 into 10 to minus 19 joule. First we have to find Ke max, and second stopping potential. Now first Einstein's photoelectric equation is Ke max is equal to Hc upon lambda minus phi naught. H is 6.625 into 10 to minus 34. C is 3 into 10 to power 8 meter per second velocity of light in vacuum. Lambda is 5400 10 to minus 10 minus phi naught. Phi naught is 1.9 into 1.6 into 10 to minus 19, which on simplification gives the kinetic energy as 10 joules, 0.64 into 10 to minus 19 joules. Now second part, kinetic energy or Ke max is equal to E into V naught, stopping potential, which gives stopping potential as Ke max upon E. Ke max is 0.64 into 10 to minus 19 upon E is 1.6 into 10 to minus 19. So stopping potential will be 0.4 eV. This cancels out. 0.4 volts. Next question. Light of frequency 5 into 10 to power 14 Hertz liberates electrons of energy 2.3 into 10 to minus 19 joule from a metal surface. What is the wavelength of ultraviolet light which liberates photoelectron of energy 8.93 into 10 to minus 19 joule from the same surface? Now, in this question we have two cases. For case 1, Ke1 will be equal to Hf1 minus phi naught. Suppose this is equation 1. And for case 2, Ke2 will be equal to Hf2 minus phi naught, equation 2. Equation 1 minus equation 2 gives Ke1 minus Ke2 is equal to Hf1 minus F2, as phi naught gets cancelled. Therefore, we get F1 minus F2 is equal to Ke1 minus Ke2 upon H, and therefore F2 will be equal to F1 minus K1 minus K2 upon H, and on putting the values we get F1 is 5 into 10 to power 14 minus K1 is 2.3, K2 is 8.93, and 10 to minus 19 is common to both upon H. H is 6.62 into 10 to minus 34. On simplification we get F2 as 1.5 into 10 to power 15 Hertz. Now F2 will be equal to C upon lambda 2. Therefore, lambda 2 will be equal to C upon F2. C is 3 into 10 to power 8, and F2 is calculated to be 1.5 into 10 to power 15, which gives wavelength required as 2 into 10 to minus 7, 2 into 10 to power minus 7 meter. Next question is, when light of frequency 5.4 into 10 to power 14 Hertz is incident on a metal surface, the maximum kinetic energy of emitted photoelectrons is 1.2 into 10 to minus 19 joule. If the same surface is illuminated with light of frequency 6.6 into 10 to power 14 Hertz, the maximum kinetic energy of emitted photoelectron is 2 into 10 to minus 19 joule. Find the value of Planck's constant. Here we have two cases. Therefore, for first case, for case 1, photoelectric equation will be Ke1 minus is equal to Hf1 minus phi naught, equation 1, and for case 2, Ke2 will be equal to Hf2 minus phi naught, equation 2. So, if you subtract equation 1 from equation 2 from equation 1, we get Ke1 minus Ke2 will be equal to H taken common, F1 minus F2. Therefore, H will be equal to Ke1 minus Ke2 upon F1 minus F2. The values of Ke1 and Ke2 are 1.2 into 10 to minus 19 minus 2 into 10 to minus 19. 10 to minus 19 is common to both. Similarly, F1 has value 5.4 into 10 to power 14, and F2 has value 6.6 into 10 to power 14. 10 to power 14 is common to both, and on simplification we get Planck constant as 6.66 into 10 to minus 34 joule second. Next question number 8 is, photoelectric threshold wavelength of tungsten metal is 272 nanometer. Calculate the maximum velocity of photoelectron emitted. Photoelectron when photon of frequency 1.45 into 10 to the power 15 Hz is incident on the tungsten surface. Planck constant is given. Solution: K max is equal to H F minus pi naught. K max may be written as 1 by 2 m v max square, maximum kinetic energy of photoelectron. This is H F minus pi naught is Hc upon lambda naught. Therefore, V maximum will be equal to 2 under root 2 Hf minus Sc upon lambda naught upon m. Or here H may be taken common. 2 H is 6.62 into 10 to minus 34. F is 1.45 minus into 10 to the power 15 minus Hc upon lambda. Or therefore B max will be equal to under root 2 H may be taken common and its value is 6.62 into 10 to minus 34. F is 1.45 10 to power 15 minus C. C is 3 into 10 to power 8 and lambda naught is 272 nm means nanometer 10 to minus 9 meter upon m, mass of electron 9.1 into 10 to minus 31 kg, because lambda naught is 272 nm, which is 272 into 10 to minus 9 meter. And on simplification we get the velocity as 7.1 into 10 to the power 5 meter per second. Next question number 9 is maximum kinetic energy of photoelectron emitted from a surface with light of wavelength 400 nanometer is 1.1 eV. What will be the maximum kinetic energy of photoelectron from the same surface with light of wavelength 300 nanometer? Here, in case 1, K1 maximum kinetic energy of photoelectron is K1 is equal to Hc upon lambda 1 minus phi naught, question 1. And in case 2, K2 will be equal to Hc upon lambda 2 minus phi naught, question 2. Equation 1 minus 2 gives K1 minus K2 is equal to phi naught cancels out, Hc is common, 1 upon lambda 1 minus 1 upon lambda 2. So we have to find the K2. We can get K2 is equal to K1 minus Hc 1 upon lambda 1 minus 1 upon lambda 2. Now putting the values, corresponding values. Ke1 is 1.1 electron volt, means 1 into 1.6 into 10 to minus 19 joule, minus H is 6.62 into 10 to power minus 34, into C 3 into 10 to power 8, into 1 upon lambda 1. Lambda 1 is 400 angstrom, 1 upon 400 nanometer, 400 into 10 to minus 9, minus 1 upon 300 into 10 to minus 9. On simplification we get Ke2 as 3.425 into 10 to power minus 19 joule. And when we divide it as therefore or Ke2 will be equal to 3.425 into 10 to minus 19 divided by 1.6 into 10 to minus 19 electron volt, which on simplification gives 2.14 electron volt. So the maximum kinetic energy of emitted photoelectron in second case will be 2.14 electron volt.